Let's solve some problems related to coloring. So one is this one. So they give you a graph and they ask find out the minimum number of colors. So there is no solution, like there is no shortcut. We have to try all possible ways. So that's why this problem is just about trying all possible ways quickly within 2 minutes. So but what I do is, whenever this kind of problem is given, to get the minimum number of colors, because there is no method, I will try in this way. I will try to share as many colors as possible. If I can do it, okay, then I might end up with the best possible solution. So what is my idea is, try to color this graph with as less number of colors as possible. Further, try to share wherever you can share the colors. Let's begin here. Okay, let's label them A, B, C, D, E, F, G, H. So for vertex A, I give color number 1. Okay, and after that I try to share this color in as many places as possible. Where can I share this color? I can share a color 1 to here, right? Then can I share anywhere? If I share here, then I can't share here because adjacency. I can't share here, I can't share, I can't share, I can't share, I can't share. So in 2 places I can share. Now quickly what comes to my mind is, so filling this position, right? Color it with 2 because it's a symmetric structure. Probably if I color here with same, then probably I can share the colors, right? So again, color 2 I kept here and I shared here. I'll try to share this color in any other way, like here I can't because it's adjacent. So now you realize that this color 2 cannot be given anywhere. After that, let's try to bring one more color. So 1 2, however triangle requires one more color, right? Let's keep 3 here, then try to share it. Can I share here? No. Here? No. But here, yes. So successfully color 3 also shared in so many places, like at least 2 places. Now we have 2 more vertices to be colored. If I give here 1 problem, 3 problem, 2 problem, then give a different color 4. Try to share it. Yes, I can share it. Now you see, I have colored this graph with 4 colors. Okay, so and slowly you realize that let's try with 3, but whenever you try with 3 colors you fail. Okay, so in the gate exam, so try like this and you will get answer with 4 colors. That means you can color it with 4, but whatever the way you try with 3 colors you can't do it. Then you can understand that minimum number of colors required is 4. Okay, 5 is definitely not the answer, 2 is definitely wrong. Answer either 3 or 4, because with 4 I have shown you, and try with 3 but you don't get it. Okay, so it's a trial and error problem. That's why I can't explain more than this. We have to try all possibilities. Okay, we'll see one more problem. How many ways the below graph can be colored if at most 4 colors can be used? Okay, you can use only 4 colors. Let's do it. It's a combinatorics problem. Let's start at some vertex A. Okay, how many different ways you can color this vertex? Since you have 4 colors, let's say they are red, green, yellow, blue, then you can color this position with 4 ways, right? Then come and color this one. Let's say I'm doing systematically. First I color A, after that color B, after that color, let's say D, after that color C. If I do that, what happens, we'll see. How many different ways you can color B now after coloring A? Since you can't use the same color which is used in position A, then you will have 3 ways, isn't it? So now 2 vertices are colored. Come to D. Since B is already colored and A and D are unrelated, then you can take the color of A, not an issue, right? Only the condition is you can't use color of B. Then how many different ways you can color it? Other than B's color, there are 3 colors. So anything I can use, then 3 ways, right? So far so good. 4 into 3 into 3. Now when it comes to C, there is a problem. C is adjacent to A and D, right? Then how many colors C require? We have to color C with any color other than color of A, color of D. What case number 1 you see? In case number 1, what can happen is, let's say vertex A takes red color, vertex D also takes red color. That is possible. That means A comma D share same color, like red comma red. Is it not possible? Yes, it's possible. That means I want to why this, the significance of red is to say that these two have same color. Okay, then C cannot use that red color. Apart from that, anything it can use, then C can be colored in three ways. In that case, okay, let's write three ways. Case number 2. In case number 2, what if A takes red color and D takes green color? That is also possible because you said three ways, right? Other than this, any of the three ways if you color, probably you can use different color than red, then maybe green. In that case, so C cannot use red, C cannot use green. Overall four colors are there, two are gone. Then only two ways we can color that one. Now that's why A can be colored with four ways unambiguously, B can be colored in three ways unambiguously, D can be colored in three ways unambiguously, but C cannot be colored in three ways. Correct? It's absolutely wrong because it's sometimes three ways, sometimes two ways. So when you have this kind of dilemma, then do the problem in cases. Okay, first of all, solve case number 1, after that case number 2. Okay, let's color the graph such a way that case number 1 happens. Okay, so I'm coloring my graph so that case number 1 happens. So in case number 1, remember A comma D should get same colors. Okay, same color, maybe red, green, anything. Remember that in your brain. Then how many different ways you can color vertex A? Four ways, right? Then how many ways you can color vertex B? Three ways, right? Other than color of A, three ways. Now how many ways you can color D? Because it is now case number 1 specially. Then A and D should have same color. Then already A is colored, example it uses red, then you have to use same, then you don't have option Mr. D, then you will be colored only one way. Now come to C. In this scenario, so A and D has same color, then other than that anything you can use, then three ways you can color. So these are all colorings where A and D has same color, right? Now go to the second case. What is that second case? The second case is same graph A, B, C, D, but this time case number 2. That means A comma D doesn't have same color. That means different colors. Let's try that. If A comma D have different color, what happens we'll see. So how many ways you can color A? Four ways. Then how many ways you can color B? Same three ways. Now how many ways you can color D? Since A and D are different, now if example A uses red color, then don't use that red, you have to use different color. Then you can't use B's color also, then don't use A's color, don't use B's color, then only D will become different. Then this will be two ways, right? Any of the two colors we can use. Then come to C. How many ways you can color C? Since again C cannot use color D, C cannot use color of A, then remove that 2. Then out of 4, if I remove 2, then any other two ways we can color. Why this time 2? Why not 3? Here A comma D has same color. So other than that you used anything, but here A comma D have different colors, let's say red and green. Remove them from overall 4 colors, then remaining ways are only 2 ways. Then how many different ways you can color this graph is 4 into 3 into 2 into 2. How many ways you can color the graph in this model is 4 into 3 into 1 into 3. So total number of ways are either these ways or this ways. So we have to sum it up. So answer will be 4 into 3 into 1 into 3 plus 4 into 3 into 2 into 2. If I simplify it, you get 3 3 is a 9, 4 is a 36 plus probably 12, 24, 48. So it will be 54 and 84. So 84 ways you can color this graph if you have 4 colors. Let's solve one more problem related to coloring. A graph is given with 6 vertices and chromatic number is 3. What is chromatic number? Minimum number of colors required to color that graph. That is 3. Then maximum number of edges it can have. So what I do is first I explain this graph with vertices A, B, C, D, E, F. There are 6 vertices. So and chromatic number of graph is 3. Then probably whatever the way you color this one, then at least 3 colors are required. Let me color this graph with 3 colors. Let's say just possibility I am talking about. Let's say 1, 1, 1. I give color 1 to 3 vertices, color 2 to 1 vertex, and color 3 to let's say 2 vertices. Okay. Then In such graph, how many maximum edges we can have? That's the question. What you do is, to understand this concept clearly, I create three partitions. This for all are for vertices. This is for color 1 vertices. This is for color 2 vertices. This is for color 3 vertices. Let's keep all the color 1 vertices here A, B, C, and all the color 2 vertices D, comma E. I am redrawing the graph so that I can easily count the number of edges. So there is only one vertex with color 2, right, D, then E comma F in color 3. Since you can't add an edge between A to B or A to C, then whenever the question is maximum number of edges, so maximum number of edges you can draw, or any edge you can draw only from one partition to another partition. So how many edges you can draw from here to here? That will be 3, right? So that's why 3 into 1. The size of this partition is 3. The size of this partition is 1. The size of this partition is 2 in this example. Okay. So it's not compulsory to have 3 vertices of color 1 in that way. Okay. So we are thinking about a possibility, or we are trying one possibility. So 3 into 1 plus. So what if you have one vertex here, two vertices? How many edges you can draw? 2, right? 1 into 2 plus these two vertices to these three vertices, how many edges you can add? 2 into 3, right? So overall edges for this structure is 3 plus 2 plus 6. It will be 11. Okay. Can we have better possibility? Right. For that we have to change the structure of the graph. Let me change the structure of the graph. So for that I take color 1 vertices as A comma B, color 2 as CD. That means I am equally distributing them. So I will tell you the reason why I am equally distributing them. Whenever I equally distribute the vertices, what happens is, if I keep all the vertices in one partition, then you are restricting yourself to not add lot of edges, right? When more vertices in one box, less number of edges you can add, correct? So that's why don't try to keep all the vertices in one box. For that we have to distribute vertices into partitions equally. That will be the best possibility, so that I can have lot of edges. Example, you see here you have two vertices, two vertices, two vertices. In this possible scenario, maximum number of edges you can add is 2 into 2, right? B, D, A, C, in that way, 2 into 2. Similarly, plus here to here you can add again 2 into 2, 4 edges. Now, the color 3 to color 1, 2 into 2. It will become 4 plus 4 plus 4, which is nothing but 12. It is better than 11, isn't it? So if you want to try, you can try this also. All four vertices like A, B, C, D in one place, E in one place, F in one place, where you are keeping lot of vertices in one partition. Then you see what happens. So easily we can say that this is not maximum possibility. Why? These four vertices cannot share edges among themselves, right? Then you are restricting the graph to, so that not to have very, large number of edges. So that's a problem. You can check it out easily. So 4 into 1, right? Only 4 edges. 1 into 1, only 1 edge. Plus 1 into 4, 4 edges. It will become 4 plus 4, 8 plus 1, 9. So it is reduced it to minimum, right? So that's why maximum number of edges it can have is 12. The possibility is 2, 2, 2. Now once you solve this problem, it takes lot of time first time, but next time if this kind of problem is given, example with value, let's say 10 or 8. Otherwise let's take 9, so it is equally divisible. So when there are 9 vertices and same problem is given, take 3 boxes. Now we know that every partition should have equal number of vertices. Then keep 3, 3, 3. Then you can do like this. Here to here 3 into 3, 9 edges. Here to here 3 into 3, 9 edges. Here to here 3 into 3, 9 edges. Overall total number of edges are 9 plus 9 plus 9, 27. In that way easily we can answer this kind of questions.